Hello my friends, and welcome back to the You Can Do TV channel. The 600 HP Snow natural gas pumping engine at the Cool Spring Power Museum, as demonstrated in June 2013, represents a remarkable achievement in historical industrial preservation. This particular video documents the startup, brief operational run, and controlled shutdown of the massive horizontal engine. Originally designed for natural gas transmission applications, the Snow engine is a two-stroke, single-cylinder machine featuring an integrated compressor driven by a crosshead mechanism. The demonstration marked the fourth successful startup since the engine's extensive restoration began, following years of disassembly, inspection, machining, and meticulous reassembly carried out by museum staff and volunteers. In this specific run, additional mechanical calibrations were implemented, including refinements to the valve timing and manual adjustment of the fuel gas admission system. The engine, fueled by natural gas, required careful synchronization between ignition, intake, and exhaust phases. The startup procedure involves manually barring the engine to position the piston, priming the lubrication circuits, opening the fuel valves, and initiating spark ignition. Once in motion, the engine's immense flywheel and crankshaft generate significant rotational inertia, allowing smooth and sustained operation under minimal load. The volunteers had also fine-tuned the pressure regulators and monitored crankcase temperatures to ensure safe operational limits. The shutdown phase consisted of fuel cutoff and residual rotation until the engine coasted to a complete stop. Observers were able to inspect the rhythmic operation of the exposed mechanisms, including rocker arms, valve push rods, and the cylinder lubrication system. This live demonstration not only showcased the engine's robust design and mechanical reliability, but also served as a testament to the dedication and technical skill of the restoration crew. Their achievement preserves a key chapter in American gas industry history, ensuring that future generations can witness and learn from such engineering marvels in action. The Kempton Park steam engines, also known as the Kempton Great engines, are two enormous triple-expansion steam engines built by Worthington Simpson between 1926 and 1929. Located at the Kempton Park Waterworks in Middlesex, London, these engines are comparable in size and design to those used on the RMS Titanic, each rated at about 1,008 horsepower. Their primary function was to pump up to 19 million gallons of water per day, supplying North London with clean drinking water, sourced from the River Thames. These engines are notable as the largest triple-expansion steam engine still operational in the world. Each engine consists of 3 cylinders of increasing size, arranged to allow steam to expand progressively and maximize efficiency. The steam first enters the high-pressure cylinder, then expands into the intermediate pressure cylinder, and finally into the low-pressure cylinder before being exhausted. This multi-stage expansion extracts the maximum energy from the steam, resulting in improved fuel efficiency compared to single-expansion engines. After more than 5 decades of continuous operation, these engines were retired in 1980. Subsequently, a dedicated team of engineers and volunteers undertook extensive restoration efforts to return one of the engines to working condition. During startup, the Baring engine is engaged to rotate the massive flywheel slowly. This rotation is critical to position the pistons accurately for the admission of steam, ensuring smooth engine startup without mechanical stress. The restoration of the Kempton Park engines represents a significant achievement in industrial heritage preservation. Their continued operation offers valuable insight into early 20th century steam technology and water supply infrastructure, showcasing the engineering skill and craftsmanship of the era. Today, the engines serve as a powerful reminder of the Industrial Revolution's legacy and the vital role steam power played in urban development. In 2011, the two Smith-Man main engines of the MSB Elbe were started up for the first time after an extensive restoration period lasting over 8 years. These engines power the historic sea tug Elbe, originally built by Smith International. The restored vessel is now moored in the historic outer harbor of Maassluis, proudly representing the strong maritime heritage of the tugboat harbor. The Elbe, over 55 years old, has had a distinguished career, including service as a tug, a pilot station ship in Canada, and a well-known chapter as a Greenpeace vessel. Following meticulous mechanical and structural restoration, the original SMIT MAN main engines have been fully refurbished and successfully recommissioned. The startup procedure involved detailed inspection, lubrication, and gradual introduction of fuel and air to the main engines, ensuring all components operated smoothly. The engines are diesel-powered, known for their robust construction and reliability, making them suitable for heavy towing operations. The restoration process included comprehensive overhauls of the engine cylinders, pistons, fuel injection systems, and cooling mechanisms. Modern diagnostic tools were used alongside traditional mechanical expertise to ensure precise alignment and optimal performance. The successful startup underscored the skill and dedication involved in preserving historic marine propulsion technology for future generations. This revival marked a significant milestone, not only preserving maritime history, but also demonstrating advanced restoration techniques applied to aging marine machinery. The MSB Elbe stands as a testament to engineering durability and heritage conservation, now once again operational at the quay of its former owner, symbolizing a bridge between past maritime practices and present-day preservation efforts. The Kempton Park steam engines, housed at the Kempton Park pumping station in London, are the world's largest fully operational triple-expansion steam engines. Built between 1926 and 1929 by Worthington Simpson, each engine stands nearly 62 feet tall and weighs over 800 tons. Rated at 1,008 horsepower, they were originally designed to pump 19 million gallons of drinking water per day from the River Thames to North London. The engines are configured with high, intermediate, and low-pressure cylinders, operating in sequence, optimizing steam expansion and maximizing thermal efficiency, typical of early 20th century waterworks design. During demonstration runs, steam generated by a modern boiler is admitted into the high-pressure cylinder, then successively expanded in the intermediate and low-pressure cylinders before exhausting. Each engine features a massive flywheel 32 tons in weight and 27 feet in diameter, stabilized by a barring engine during startup for correct piston alignment. The valve gear uses a Stephenson reversing link to regulate steam flow and enable reversing. The restoration of engine number 6, completed by dedicated volunteers, allows the public to witness the immense scale and mechanical elegance of these industrial giants in motion. Kempton remains a unique heritage site, where historical engineering continues to operate under live steam, offering educational and tech. The Big Red Coreless steam engine, a centerpiece at London's Science Museum, is a cross-compound textile mill engine built in 1903 by Burnley Ironworks for the Finchley View Mill in Harlesike, Lancashire. Rated at 700 horsepower, it powered up to 1,700 looms via complex line shafting systems until its retirement in 1970. Operating at 160 psi, 11 bars, the high-pressure steam enters the HP cylinder, expands, then continues to the LP cylinder before reaching the condenser. The resulting condensate is pumped back into the boiler, improving thermal efficiency. Both cylinders use Coreless valve gear for precise steam control. The inlet valve's cutoff timing is governed by a centrifugal governor with flyballs connected to a linkage that twists a control shaft. As engine speed increases, the governor reduces inlet timing, conserving steam and maintaining speed stability under varying loads. Tripping mechanisms actuate segment gears and pawls, rapidly closing valves with dashpot cushioning. Although the LP cylinder does not require precise valve control due to operating on expanded steam, it uses Coreless gear for mechanical balance. The engine is started by a barring engine which aligns it for safe initial rotation. It was restored and installed in 1979 by Riley and Son Limited. This 1904 air blast injection diesel engine is a remarkable piece of early internal combustion technology, built by Grazer Wagen and Maschinen Fabriks Aktiengesellschaft in Graz, Austria, following drawings provided by Mann. Designed to operate as a hospital lighting plant, it was installed in October 1904 and powered a 110 volts DC Crompton dynamo and switchboard. The engine produced 16 horsepower at 235 revolutions per minute, with a bore of 215 millimeters and a stroke of 340 millimeters. Its design includes a massive flywheel to stabilize the rotation and ensure a steady power output for the sensitive electrical systems of the era. The engine used air blast injection, a system in which compressed air forces the fuel into the combustion chamber, an early approach that preceded high-pressure direct injection systems. After its service in the hospital, the engine was repurposed in a sawmill, where it continued operation until it suffered a compressor failure caused by a lubrication oil explosion. The failure resulted in internal damage to the compressor system, rendering the engine inoperable without extensive restoration. Despite the incident, the engine remains a rare survivor of pre-World War I diesel technology, representing a transitional period in engine development where robustness, manual control, and engineering craftsmanship were paramount. Today, it stands as an extraordinary example of early diesel innovation and mechanical heritage. The steam engine of the Tonnenleger Bussard is a remarkable example of early marine engineering still in working condition. Built in 1906, the Bussard is powered by a classic reciprocating steam engine, which drives the ship's single screw propeller through a direct mechanical linkage. The engine in action is a fascinating sight. Large exposed pistons and connecting rods operate in rhythmic motion, lubricated manually by the ship's crew. During demonstration runs, can observe a variety of maneuvers including forward and reverse motion, achieved by adjusting steam admission via a reversing mechanism. The operator precisely controls the throttle and direction, using large hand-operated wheels and levers. The machine demonstrates multiple speed stages, from full ahead to slow astern, showcasing the flexibility and robustness of this 19th century power plant. Steam is generated by a Scotch marine boiler, fired by coal or oil, and the engine runs with a characteristic chuffing and hissing sound. The system requires continuous manual attention, from maintaining steam pressure to oiling moving parts. Watching the Bussard's engine in operation offers a vivid reminder of maritime history and the craftsmanship involved in steam propulsion. The Princess Daphne began her life in 1954 as the general cargo ship Port Sydney, built for Port Line. In 1975, she underwent a significant conversion, transforming into a fully operational passenger vessel. By the time of her final sea trials, Princess Daphne was regarded as one of the two oldest passenger ships still in service, a testament to the durability and engineering legacy of mid-20th century shipbuilding. The heart of the vessel's propulsion system comprised two Doxford Opposed-Piston oil engines, serial numbers 733 and 734, constructed by the Wallsend Slipway and Engineering Co. Limited of Wallsend-on-Tyne in 1954. These engines represented a unique approach to marine propulsion. The Doxford engine operates on a two-stroke cycle with opposed pistons, two pistons in a single cylinder, moving towards each other to compress air and ignite fuel without the need for cylinder heads. This design offers high thermal efficiency and reduced mechanical complexity. During the sea trials, these opposed piston engines demonstrated robust performance, delivering the power needed for reliable maneuverability and sustained cruising speeds. Despite their age, the engines maintained excellent operational condition, reflecting meticulous maintenance over the decades. These final trials not only assessed engine performance and propulsion alignment, but also confirmed the seaworthiness of the entire ship, ensuring safety systems, navigation electronics, and auxiliary machinery were fully functional. The Princess Daphne thus completed her final evaluations with dignity, her Doxford engines continuing to turn as a mechanical tribute to a bygone era of maritime engineering. The MAN 12 German Marks, built in 1903, is widely regarded as the oldest operational diesel engine in the world. Preserved by the University of Applied Sciences, Ostwestfalen-Lippe in Lemgo, this engine is regularly demonstrated by the Department of Mechanical Engineering's Piston Engine Laboratory during open house events. Manufactured by Maschinen Fabrik Augsburg-Nürnberg MAN, the 12 German Marks features a single-cylinder design with a bore and stroke large enough to yield a total displacement of 10 liters. It delivers 12 horsepower at 250 revolutions per minute, using early diesel technology based on Rudolf Diesel's original air blast injection principle. The engine uses compressed air to atomize and inject fuel directly into the combustion chamber, a method typical of pre-1920s diesel engines. A separate air compressor is required to generate the high-pressure blast, often around 60 to 80 bars, necessary for this injection system. The cylinder head includes an injector nozzle, air valve, and fuel valve, all controlled by mechanical linkages. Its robust cast-iron construction and heavy flywheel ensure smooth, stable operation at low speeds, ideal for powering generators or pumps. The B&W 2000, also known as the H.C. Orsted engine, is a large-bore, double-acting, Uniflow scavenged two-stroke diesel engine with 8 cylinders, a bore of 840 mm, and a stroke of 1500 mm. Built in 1932 and commissioned in 1933, it delivers 22,500 horsepower, 15 megawatts electrical output, at 115 revolutions per minute. The engine is 24.5 meters long, 12.5 meters high, and weighs 1,400 tons. It was originally installed to supply peak load electricity to Copenhagen, and was capable of rapid startup using compressed air at 25 bars. The engine includes a 40-ton lubrication system and water cooling via a closed freshwater circuit with seawater heat exchangers. Fuel injection operates at 350 to 400 atmospheres, while air scavenging is driven by 4 gear blowers. Although disconnected from the power grid since 2004, the engine remains operational and is demonstrated twice monthly for public viewing. Crossness Pumping Station, located in East London near the River Thames, houses 4 massive rotative beam engines, originally built in 1865. Among them, the Prince Consort engine has been fully restored to working condition and stands as the largest operating rotative beam steam engine in the world. Each engine measures approximately 68 feet, 20.4 meters, in overall length and rises to a height of 72 feet, 22 meters, making them towering examples of Victorian engineering. These engines were originally single-cylinder condensing engines designed by James Watt, but were upgraded in 1899 into 3-cylinder triple-expansion engines to improve efficiency. Steam is sequentially expanded across high, intermediate, and low-pressure cylinders. To balance the varying pressure levels and maintain uniform power output, the cylinder diameters increase from high to low pressure, with the low-pressure cylinder being the largest. One key mechanical feature is the use of Coreless valve gear, which allows for variable cutoff and improves steam efficiency through quick valve opening and closing. Another distinctive element is the grasshopper counterbeam, a variant of the classic beam engine design used to guide the motion of the low-pressure piston rod. However, because the grasshopper arrangement does not guarantee true parallel motion for all components, additional crossheads are employed on the air and water pump rods to maintain alignment and prevent mechanical stress. The Prince Consort engine represents a unique blend of historical legacy and advanced 19th century engineering. Its restoration offers invaluable insight into the technical evolution of sewage pumping systems during the Industrial Revolution, and it remains a functional monument to London's infrastructure history. The Tug Holland is powered by a 10-cylinder Stork Workspoor marine engine, a robust and reliable piece of Dutch engineering. Designed for demanding maritime applications, this engine delivers consistent performance and high torque, ideal for towing and maneuvering. Its massive crankshaft and large pistons provide the necessary force to propel the tug through rough seas. The rhythmic hum of the 10 cylinders is a testament to its mechanical precision and longevity. Maintained with care, this engine continues to power the historic vessel with strength and efficiency. The manned submarine diesel engine, built in 1944 and completed in 1945, is an 8-cylinder inline, 4-stroke unit with a displacement of 96 liters. Originally rated at 570 horsepower at 350 revolutions per minute, it was never installed in a submarine. After World War II, the Allies permitted its civilian use under the condition that its power be reduced to 400 horsepower at 500 revolutions per minute. The engine features a bore of 220 mm and a stroke of 330 mm, exemplifying robust wartime engineering. Until the 1980s, it served reliably as the power unit for an emergency generator. Today, this historically significant machine has been fully restored in Engelskirchen and is privately owned, preserved as a working example of German diesel engineering heritage. This is a short tour inside the engine room of the world's largest RORO/container ship, reveals the massive scale and complexity of marine engineering. This ship, launched in 2012, measures 240 meters in length, 37.5 meters in beam, with a maximum draft of 11.5 meters. With a gross tonnage of 51,055 and a top speed of 21.5 knots, it is powered by a formidable propulsion system. At the heart of the vessel lies the Hyundai B and W70ME main engine, a 2-stroke, low-speed marine diesel engine producing a maximum power output of 22,890 kilowatts at 108 revolutions per minute. With a bore of 700 millimeters and a stroke of 2,360 millimeters, it drives the propeller directly without reduction gearing, ensuring high efficiency for long-haul voyages. Supplementing the main engine are 4 Yanmar 26 LW auxiliary generators, each delivering 1,820 kilowatts at 720 revolutions per minute. These 4-stroke diesel engines have a bore of 260 millimeters and a stroke of 385 millimeters and provide electrical power for onboard systems. The vessel also features steam generation systems, including a Sake FMB7 auxiliary boiler with a steam capacity of 2,500 kilograms per hour, and an exhaust gas economizer, which recovers heat from engine exhaust to improve thermal efficiency. Built in 1932 by Burmeister and Wayne in Copenhagen, the 884 German Mark's WS-150 was, for over 3 decades, the largest diesel engine in the world. Designed primarily for stationary power generation and ship propulsion, this 8-cylinder, 4-stroke engine delivers a continuous power output of 15,000 kilowatts, 22,500 horsepower, at 120 revolutions per minute. Standing over 24 meters long, 12 meters high, and weighing approximately 1,400 tons, the engine features direct injection and forced lubrication systems. Its cylinders, each with a bore of 840 millimeters and a stroke of 1,500 millimeters, were engineered for high thermal efficiency and minimal mechanical wear. The 884 German Mark's WS-150 was constructed using heavy cast steel components with a massive crankshaft driven by crosshead pistons and twin flywheels, ensuring stable operation. The engine is manually started via compressed air injection into selected cylinders, while auxiliary systems manage cooling, oil circulation, and fuel delivery. Despite its age, the engine remains operational and is routinely demonstrated at the Dieselhaus Museum in Copenhagen, serving as a testament to early 20th century heavy-duty diesel engineering. The Eleonora Maersk is a large container vessel with a length overall of 397.71 meters, a molded breadth of 56.4 meters, and a maximum draft of 16.02 meters. It has a container capacity exceeding 15,550 TEU and achieves a maximum speed of 25.7 knots. The vessel's main deck offers access to key operational zones, including the navigation bridge equipped with advanced control systems. Below the superstructure is the engine control room, responsible for monitoring all propulsion and auxiliary systems. The main engine is a Wartsila Sulzer 1.4 RT Flex 96C, delivering 80,080 kilowatts, 109,000 bhp, at 102 revolutions per minute. Additional engine room compartments include the workshop, located on the 8th deck, which supports maintenance and technical operations. The shaft tunnel, positioned at the lower aft section, contains the shaft line that transmits torque from the main engine to the propeller, playing a critical role in vessel propulsion and maneuvering. The engine room tour of a modern eco-class medium-range (MR) product tanker such as the M/T Bayate provides insight into the highly engineered systems that ensure fuel efficiency, environmental compliance, and reliable marine propulsion. With a cargo capacity of approximately 330,000 barrels, this vessel is optimized for transporting refined petroleum products while minimizing emissions and energy loss. Central to the propulsion system is the main engine, a MAN B&W 6G50 MEC 9.3B, a 6-cylinder, long-stroke, electronically controlled 2-stroke diesel engine. Designed for improved fuel economy and reduced NOx emissions, this ME-type engine eliminates the need for a traditional camshaft, using electronic actuators to precisely manage fuel injection and exhaust valve timing. Operating at low RPMs, typically around 105 to 120 RPM, it provides direct drive to the fixed-pitch propeller, ensuring efficient power transfer with minimal vibration and mechanical loss. Electrical power is provided by 3-man Doosan 23/30 auxiliary diesel generator sets, each rated at 1,050 kilowatts. These medium-speed 4-stroke engines supply power for the vessel's electrical grid, supporting critical systems such as navigation, communication, accommodation, cargo pumps, HVAC, and ballast water treatment. The Engine Control Room, ECR, is located adjacent to the main machinery space, and is equipped with digital monitoring stations for real-time diagnostics of engine performance, fuel consumption, exhaust emissions, and alarms. Engineers monitor the vessel's operating parameters continuously, ensuring compliance with IMO Tier 2 or Tier 3 standards, depending on the ship's Emission Control Area, ECA designation. Below the engine platform, one finds key auxiliary systems, the lube oil separators, heavy fuel oil, HFO, and marine gas oil, MGO treatment units, freshwater generators, evaporators or reverse osmosis units, and air compressors. The ship employs a centralized cooling system consisting of seawater-cooled plate heat exchangers and freshwater jacket cooling loops, providing thermal stability across main and auxiliary engines. The purifier room is isolated for safety and noise reduction, and handles oil filtration and conditioning processes. The steering gear room, located aft, houses electro-hydraulic rams that actuate the rudder via a follow-up system, receiving commands from both the bridge and ECR. Environmental protection systems are integral to the Eco Class designation. These include an oily water separator with a 15 ppm monitor, exhaust gas economizers, selective catalytic reduction, SCR units where applicable, and a ballast water management system, BWMS, designed to meet D2 discharge standards. Sewage treatment plants and incinerators are also installed. In total, the Bay State's engine room integrates advanced automation, fuel flexibility, and emission control technologies to operate within stringent global maritime environmental regulations while maintaining high transport efficiency across global trade routes. A cruise ship engine room is the heart of the vessel, housing powerful machinery that keeps the ship moving and systems running. It typically includes large diesel engines, often Wartsila or MAN, connected to generators that produce electricity for propulsion and onboard amenities. These engines can produce tens of thousands of kilowatts. The room also contains pumps, separators, HVAC systems, and monitoring panels. Noise and heat are constant, requiring extensive insulation and safety measures. Engineers monitor operations 24/7 to ensure efficiency and prevent malfunctions on long voyages. The emergency power system at the Kehlsteinhaus on Kehlstein Mountain consists of a man-built U-boat diesel engine coupled to a Siemens Schuckert electrical generator. This underground installation, inaccessible to the public, serves as a backup power source in case of municipal grid failure. The system includes a belt-driven air compressor that maintains air tank pressure, which is essential for starting the large diesel engine. The engine and generator assembly, designed for durability, continues to operate reliably after decades of service. Periodic test runs are conducted by maintenance personnel, led by Chief Engineer Herbert Eglauer, to ensure functionality. The facility was constructed between 1937 and 1938 under Martin Bormann's commission and was intended as a secure retreat and diplomatic venue for Adolf Hitler. The power system exemplifies typical bunker engineering practices, providing redundant, protected, and autonomous electrical supply. The Kehlsteinhaus is now a historical site and restaurant, with the power system preserved as part of its original infrastructure. The paddle steamer Waverly, built in 1947, is powered by a 2,100 horsepower triple expansion steam engine. This engine features a Stephenson reversing link motion, which enables smooth and precise control of the engine's direction and speed. The triple expansion design efficiently uses steam by expanding it through 3 cylinders of increasing size, maximizing power output while conserving fuel. The engine drives the paddle wheels, providing propulsion for the vessel. Additionally, the Waverly is equipped with a capstan, a vertical axle rotating machine, used for handling heavy ropes or anchors. During the event from April 30th to May 1st, 2004, the engine and capstan were showcased, highlighting the robust engineering and mechanical reliability of this historic steam-powered vessel. The startup sequence of the British Polar M45M main engine aboard the motor tug Kent showcases a robust medium-speed, 4-stroke marine diesel engine design. The M45M was manufactured by British Polar Engines Limited, a renowned British builder of compact and reliable marine engines, commonly used in tugs and small commercial vessels. Designed for durability and ease of maintenance, the engine is manually started using compressed air, with control levers to manage fuel delivery and engine timing. Once the air start system is engaged, the engine's flywheel begins to turn, followed by combustion in the cylinders, as fuel is introduced sequentially. In addition to the main propulsion engine, the tug is equipped with 2 Lister JP2 auxiliary generators. These are 2-cylinder, air-cooled diesel engines, known for their rugged design and steady output. During startup, they produce a distinctive rhythmic exhaust beat, providing essential electrical power for onboard systems, lighting, and communications. These generators are manually cranked or started with compressed air or electric starters, depending on configuration. The combined system demonstrates practical, proven marine engineering suitable for extended operations in both coastal and open water conditions. The startup procedure emphasizes mechanical simplicity and operator involvement, hallmarks of classic British marine engine design. The first start of the Continental R975 radial engine marks a key milestone in the full restoration of the M4A 176mm horizontal volute spring suspension, HVSS Sherman tank. Originally designed as an aircraft engine, the R975C4 was adapted for armored vehicle use due to its compact dimensions, high power-to-weight ratio, and air-cooled simplicity. This 9-cylinder radial engine delivers approximately 400 horsepower at 2,400 RPM and was widely used in various Sherman variants during World War II. Following a comprehensive mechanical overhaul, the engine is bench tested to verify oil pressure, ignition timing, fuel delivery, and proper valve function. Upon ignition, the characteristic radial firing sequence creates a unique sound profile and smooth rotation, confirming internal synchronization and combustion health. The successful startup confirms the integrity of the rebuild, paving the way for engine integration into the chassis of the M4A1. The HVSS variant of the Sherman allows for improved ride and handling, making it one of the most advanced iterations of the series. This engine test is not only a technical checkpoint, but also a tribute to wartime engineering and restoration craftsmanship. On May 16, 2019, Southland Holdings conducted a full operational test of their 15.5-foot diameter tunneling machine, a critical milestone prior to deployment on a large-scale infrastructure project. The test was designed to evaluate all key systems under load, including the rotating cutter head, main drive motors, hydraulic systems, and conveyor operations. The machine, a single-shield tunnel boring machine, TBM, was engineered for soft ground and mixed-face conditions, equipped with a high-torque main bearing and segmented cutter head designed to efficiently break through variable geologies. The test procedure involved activating the cutter head at controlled rotational speeds while simulating advanced thrust and screw conveyor discharge. Engineers monitored the machine's instrumentation closely to ensure alignment, pressure distribution, and mechanical integrity under operating parameters. Electrical power consumption, hydraulic fluid flow, and vibration data were logged in real time to verify component performance and identify potential failure points. Additionally, articulation and shield control systems were exercised to simulate navigation through a curved tunnel alignment. The test confirmed that the TBM met required safety and performance standards and was declared ready for launch. This trial ensured the reliability of all operational subsystems before full-scale tunneling operations commenced. The engine room of the FSO crude oil tanker, with a gross tonnage of 59,289 t and a dead weight of 115,232 t, houses a MAN B and W6 S60 MC low-speed, two-stroke main engine rated at 13,820 bhp at 92 rpm, 10,305 kilowatts. This engine directly drives the fixed-pitch propeller via a robust propeller shaft, supported by shaft bearings and an A-frame structure. Key engine components include the cylinder heads, camshaft, exhaust valves with hydraulic actuation lines, fuel oil pumps and injectors, crankcase doors, piston cooling oil feeds, yellow coating, scavenge drains, red valve, and scavenge inspection covers. The exhaust manifold, fitted with an automatic air valve, channels exhaust gases into the high-efficiency turbocharger, operating at speeds up to 15,000 rpm. Three SsangYong MAN B and W diesel generators, each delivering 650 kilowatts, 850 kVA, are coupled to alternators and managed through local control panels. Generator synchronization and load sharing are handled in the engine control room, ECR, which also includes 220 volts / 440 V feeder panels, generator breaker controls, boiler pressure indicators, tank level monitoring, inert gas alarm panels, and a Kongsberg engine room surveillance system. Steam generation is supported by two AQ9 auxiliary boilers rated at 16 bars and one AQ16 composite boiler rated at 7 bars. Composite boiler operations involve purging, fuel oil valve activation, burner ignition, and feed water circulation. Boiler feed systems comprise horizontal feed pumps, a feed water tank / hot well, a cascade tank, and an atmospheric steam condenser, blue cylinder above. Steam is distributed via a reducing station, 16 to 7 bars, for tank heating, stripping pumps, and auxiliary services. Furnace sight glasses and soot dosing access ports enable combustion monitoring and soot blowing routines. The air system includes two-stage reciprocating compressors, 30-bar air receivers, and a local start/stop panel. The emergency charge air blower and charge air cooler serve the main engine. Freshwater generators, utilizing jacket water or steam, each produce up to 16 tons per day. The vacuum condenser receives exhaust steam from the two 2.5 megawatts cargo pump steam turbines, which are fed via governor-controlled throttle valves and equipped with steam stop valves, drain systems, and lubricating oil cooling. Additional equipment includes HT and LT cooling pumps, lubricating oil coolers, air ejectors, refrigeration compressors, and air conditioning units. The turbine shaft connects down to centrifugal cargo pumps located in the pump room, completing the oil transfer system. Overall, the engine room integrates propulsion, power, steam, cooling, air, and cargo support systems, ensuring autonomous and efficient offshore crude oil storage and transfer operations. The engine room tour on board the Mount Ivor Expert, a 46,000-ton product tanker built in 1997, offers a comprehensive glimpse into the ship's mechanical and operational heart. At the core of its propulsion system is a MAN B and W6S50 MCC low-speed diesel main engine, which drives the single fixed-pitch propeller efficiently over long voyages. The tour begins at the changing room and proceeds through the air compressor stations, including starting air compressors and a working air compressor with its reservoir. The engine control room serves as the brain of operations, featuring the main switchboard and diagnostic systems. Adjacent is the electrical workshop, where engineers maintain and troubleshoot electrical systems. The steering gear room houses hydraulic systems responsible for maneuvering the rudder. The vessel is equipped with an oil-fired auxiliary boiler for onboard heating and steam generation. The fuel valve test room and spare parts storage ensure engine maintenance readiness. Notable components include the main engine's exhaust valves, turbocharger, and exhaust gas receiver, all vital for managing engine performance and emissions. The high-temperature freshwater cooling pumps and freshwater generator maintain thermal and potable water systems. Inside the purifier room, heavy fuel oil is cleaned before combustion, supported by a network of fuel oil heaters and pumps, servicing both main and auxiliary engines. Main seawater cooling pumps regulate thermal loads from machinery. The escape trunk offers an emergency egress path. Further highlights include the bilge water separator, main engine shaft and shaft seal, crankcase access, and scavenging air cooler. Walking up toward the funnel reveals air intake fans for the inert gas generator and one of the 4 engine room ventilation fans. An exhaust gas boiler utilizes waste heat from the engine for auxiliary steam generation. A spare piston, nearly half a meter in diameter, is also kept on board as a critical component for major engine overhauls. The Ivor Expert's engine room showcases a sophisticated integration of mechanical systems, safety equipment, and energy optimization measures, representing the standards of product tankers in the late 1990s. The engine room also houses the shaft tunnel, where the main engine shaft and shaft seal are located, ensuring propulsion power is transmitted smoothly to the propeller. Emergency systems like the escape trunk and firefighting equipment are strategically placed to enhance safety in critical scenarios.